Loop quantum gravity, weird science and philosophy mind-benders. In the grand, gallivanting gallop of scientific endeavour, few quests are as captivating, as conceptually colossal, or as curiously compelling as the pursuit of quantum gravity. Picture, if you will, dear viewer, the glorious stage of space-time as an infinite, silken curtain billowing gracefully across the cosmic theatre upon which the drama of planets, stars and galaxies unfolds. Now imagine that curtain isn't smooth at all, but rather a frenetic, ever-shifting patchwork of tiny, twirling loops, each one a stitch in the fabric of reality itself. This, in essence, is the wild, woolly and wonderfully weird world of loop quantum gravity, LQG. A theory that takes the elegant continuity of Einstein's space-time and shatters it into a billion quantum fragments. Science, ever the meticulous architect, scrutinizes LQG's equations with a furrowed brow, searching for the hidden blueprints of the cosmos. Philosophy, meanwhile, that mischievous horsefly of human thought, buzzes around, asking impertinent questions like, but what does it all mean? And is reality itself just a cosmic game of connect the dots? Together they turn LQG into one of the most thrilling, frustrating and downright mind-bending ideas in modern physics. Warning: this video may contain traces of pretentious vocabulary, meandering metaphors, intentional alliteration, and a sleep-inducing monotone narration. You're welcome! Part 1. The science of spacetime's quantum quirks. At its core, LQG is a radical reinvention of spacetime itself. Forget the old notion of a smooth, infinitely divisible void. LQG declares that space is chunky, granular and built from tiny, vibrating loops. These loops intertwine like an endless cosmic macrame project, forming a dynamic, ever-evolving network called a spin network. When these networks evolve over time, they trace out a structure known as spin foam, which sounds like something you'd find floating atop a quantum barrister's latte, but is in fact the scaffolding of reality itself. This isn't just wild speculation. LQG is born from the shotgun wedding of quantum mechanics and general relativity, two titans of physics that have long refused to play nice. Einstein's theory paints gravity as the curvature of space-time, while quantum mechanics deals in probabilities, particles, and the kind of uncertainty that would make a Kenny Rogers's gambler sweat. LQG steps in as the mediator, declaring, "What if space-time itself is quantum?" The mathematics behind this is both exquisite and exasperating. Spin networks resemble the fever dreams of a hyperactive spider, yet within their tangled lines lie profound truths. Black holes aren't bottomless pits of doom. They reach a smallest possible size before, perhaps, bouncing back in a cosmic, no way, not today moment. LQG suggests that the event horizon of a black hole, the point of no return, is not a smooth, featureless surface, but a fuzzy, frothy fringe composed of discrete, quantized loops of space-time. The Big Bang might have been a big bounce. Loop quantum cosmology, LQC, a direct application of LQG principles, paints a radically different picture in that a rebound from a previous universe's collapse, like a phoenix rising from its own mathematical ashes, gives rise to a new universe. Space itself comes in indivisible chunks, meaning you can't slice it infinitely thin. There's the smallest possible piece, a plank-sized pixel of reality beyond which even Zeno's paradox throws up its hands and quits. Time, too, is not an eternal, unbroken river, but a shimmering, staccato sequence of quantum tick-tocks. Yet for all its brilliance, LQG has a glaring, gremlin-sized problem which is no direct experimental proof. Unlike the triumphant detections of gravitational waves or the Higgs boson, LQG's predictions remain tantalizingly out of reach, lurking in the shadows of Planck-scale physics, waiting for some future Einstein or a sufficiently sensitive telescope to drag them into the light. Part 2. philosophy's deep dive, reality, relationalism, and the quantum quandary. This brings us to the fertile, fascinating fields of philosophical inquiry that LQG so richly cultivates. If science is the how, philosophy is the insatiable child who never stops asking, but why? And when it comes to LQG, the questions get gloriously strange. Spacetime, real or just a really convincing illusion? Philosophers like Immanuel Kant considered space and time as necessary conditions for human perception, fundamental scaffolds that our minds impose upon the external world. But LQG presents a startling counter-argument. What if space and time are not fundamental at all? Classical physics treats space-time like a static stage, an unchanging backdrop for the universe's drama. LQG, however, says the stage is built from quantum Legos, constantly snapping together and apart. This throws a wrench into eternalism, the idea that past, present and future are equally real. If time itself emerges from the interactions of spin networks, does now even exist at the most fundamental level? Or is it just some useful fiction like a troll bridge or your gym membership? Causality. Do quantum dominoes play by the rules? In the smooth, continuous world of classical physics, cause and effect are neat and orderly, such as dominoes falling in a line. But if reality is pixelated, what happens to those dominoes? Do they teleport between Planck-sized gaps? LQG suggests causality still holds, but in a fuzzy, quantum-approved way, like a game of telephone played by subatomic particles with a slight hearing impairment. Leibniz's revenge. Is space just a fancy web of relationships? The philosopher Gottfried Leibniz once argued that space isn't a thing, but a collection of relationships between objects. It's a cosmic, it's not where you are, it's who you're next to scenario. LQG, with its spin networks, seems to agree. There's no fixed grid, no absolute background, just an ever-shifting dance of connections. This makes LQG the darling of relationalists, who've been waiting centuries for physics to catch up to their worldview. The measurement problem's rowdy sibling. How does smooth space-time emerge from quantum jitters? Quantum mechanics already has the infamous measurement problem, which means, how do probabilistic waves collapse into definite outcomes? LQG adds a new layer of mystery. How does the smooth, continuous space-time we experience emerge from a jittery, discrete quantum foam? Some say it's decoherence, quantum weirdness, averaging out. Others invoke undiscovered principles. Either way, it's a riddle, wrapped in an enigma, wrapped in a spin foam placed inside Schrödinger's box that may or may not contain a cat. And this brings to mind, dear viewer, does one need to clean Schrödinger's cat box every so often to keep it from smelling? Process metaphysics in action. Theoretical physicist Carlo Rovelli leans towards process metaphysics or event ontology, which suggests that the universe isn't made of persistent things or substances that simply exist, but rather of fundamental fleeting events or processes. Reality in this light is a dynamic unfolding of interactions and changes, a ceaseless dance of becoming, rather than a static state of being. This shifts the philosophical focus from what is it to what does it do or what happens. LQG's existential questions. If space and time are not fundamental, then what are we to make of our human experiences, which are so deeply tied to them? Is consciousness merely an emergent phenomenon within this quantum framework? Does free will still hold meaning in a universe that operates on probabilistic principles at its deepest levels? Part 3. LQG versus string theory. The ultimate showdown of quantum gravity gladiators. No discussion of quantum gravity is complete without mentioning string theory, LQG's flashier, more extroverted rival. While LQG chops space-time into loops, string theory replaces particles with wiggly strings vibrating in extra dimensions. It's the difference between a minimalist sculptor LQG and a baroque maximalist string theory. Background dependence, the cosmic canvas controversy. String theory relies on a fixed space-time backdrop, a cosmic stage for strings to dance upon. LQG scoffs at this, declaring, "Space-time is part of the show." This background independence is LQG's badge of honour, though it makes calculations trickier than herding quantum cats. Predictions, or the glaring lack thereof. String theory has been mocked for making few testable predictions, though it's not for lack of trying. LQG, to be fair, is in the same boat, though its cosmological models, like the Big Bounce, offer tantalising hints that keep physicists awake at night. Philosophical fan clubs, who's cheering for whom? String theory's extra dimensions woo the mathematical aesthetes, while LQG's discrete space wins over relationalists and process philosophers. It's not just a clash of equations, it's a battle of worldviews, a duel between two visions of reality. Part 4. The Future of LQG. A theory in search of a revolution. In the grand, gorgeous garment of the cosmos, loop quantum gravity offers a captivating, conceptually compelling vision of reality. It tells us space-time isn't a smooth continuum, but a shimmering quantum quilt, forever stitching itself into new patterns. Science admires its mathematical elegance. Philosophy revels in its metaphysical implications. Yet, until experiments catch up, LQG remains a brilliant hypothesis in limbo. A theory that could either rewrite physics or fade into the footnotes of almost but not quite ideas. Either way, it's a wild ride, a cosmic rollercoaster where space-time shatters into loops and the universe whispers, "You thought you knew me? Think again." So, keep your eyes peeled and your mind open. The next great discovery might just be a quantum loop away. And when it comes, the universe might finally reveal whether it's a seamless tapestry or a dazzling, dizzying patchwork of loops. And if nothing else, LQG teaches us a valuable lesson which Ravelli once so elegantly stated: "The landscape is magic, the trip is far from being over."